All right, thanks everybody for joining, and thanks to those who've been patient with us as we go through some scheduling woes over the past couple of weeks. As the world has opened up, people are a little bit harder to schedule, so that's why we had to move this talk and the talk from Marcos, and that's going to occur in 2 weeks, a little bit, just because of shifting schedules. So we'll continue to keep people updated as we get some of those moved around. Uh, Andrew's talk today, in particular, is one that we've had a lot of requests on. People have been really interested in learning about what ESnet is doing with regards to the wireless edge services, whether it be satellite or 5G. And I can think of no better expert to talk about this, since Andrew is funded to do one of these projects and has a lot of insight into some recent deployment activities. So I'm going to throw it over to Andrew to give us an overview.
Thank you very much, Jason, and really appreciate this chance to talk. And I guess this makes me number 114 or something on the talk series. But really appreciate it.
That's about right. Yep.
Yeah. So I'm going to talk about sort of work underway to think about the wireless edge at ESnet. I'm with ESnet Science Engagement Team, so I'm going to be approaching this problem really from the standpoint of how do we think about what our customers need and how science users are using this space. And please feel free to throw in with questions at any time. So, the science motivation obviously is ESNet's mission is to provide, basically frictionless geospatial capabilities for scientists to move data however they need to. And so, while we're responsible for the optical backbone that connects all of the user facilities and, various sites within the DOE complex, to support unclassified science research. Increasingly, as scientists begin to explore advanced wireless capabilities, we need to be in that space as well. So really what I'm engaged with is sort of a research and engineering puzzle to try and figure out what are the right support models for these activities. Initially really focusing heavily on field research and scientists who are doing sort of environmental and energy work sort of off our traditional grid. But as sort of the advanced wireless field, which I'm sort of taking to writ large as meaning sort of 5G, non-terrestrial systems, millimeter wave, shared spectrum space, white space spectrum use. Really we're trying to figure out where do we want to position ESnet. And it really also, how do we, as we roll out ESnet 6 and the capabilities that we'll have on the wired side, how do we want to think about integrating those capabilities so that scientists are presented with sort of a seamless workflow for movement of data across the wireless and wired divide. And there's a ton of things sort of in the mix here. It's a huge technology space because it's not just about the wireless aspect of things. If you think about it from the user perspective in terms of making their workflows easy, you're also getting into sort of in the nature of edge compute, how HPC, high performance compute backhaul is going to work and how we're going to manage queues and resources available, intelligent network automation, ability to deploy capabilities quickly and easily, use of multiple wireless networks at the same time, depending on latency and other demands. So you're really getting into sort of a very large technology space very quickly. And really what this is about is sort of getting ESnet connected to the kinds of things that are happening off in spaces like this. This is a picture of I believe an ARM resource that's off in the mountains of Colorado. We're working with a number of different programs sort of in remote spaces. And there's both an engineering and sort of a networking challenge and all that, but it's really sort of connecting to sort of places beyond the laboratory boundary. On the science side, we're really in this really fascinating period where science itself, or earth and environmental sciences, are becoming much more interested in sort of becoming a closed loop activity, and sort of this tight coupling of models, observation, and data analytics is starting to become a more prominent part of sort of the planning among the earth scientists community, and in part it's being driven by concerns about climate change and the ability to manage scarce resources like water or handle wildfires. But it's also, because compute power allows simulations to be run at much higher fidelity, with much higher predictive power, the natural inclination starts to become to try and develop a sort of integrated campaign where you're taking measurements, you're comparing those measurements to analytic results that you expect from simulation models, and then you're using those analytics to then retask your collection capabilities, your sensors that you may have in the field, across many different modes, to more intelligently inform your hypotheses. So in order to make this all work, there's sort of three big components of the puzzle that people are working on. One is to try and figure out where in this sort of coupled network, these sort of things working together, you put edge compute. Another is to think about sort of how do you make machine learning and automate data analytics. But then the other part of it is how do I couple sensors and capabilities into this network more effectively, and that inherently gets you into wireless space as you start to think about, say, unattended or resources that are in scarce sort of environments from a power or connectivity perspective, or dynamic assets where you're starting to think about like tasking drones to do sampling, and you want to use those resources more intelligently. So this, so rapidly gets in the space where you're thinking about sort of the entire research and educational network sort of stack and how all of the components work together as an integrated instrument for science. Some of these themes were developed a couple of years back now in sort of the 5G enabled energy innovation summit, which again was sort of about 5G, but also about sort of advanced wireless. But then there's a lot of sort of other things developing. And then the cool thing is we're in this space where there's a lot of technology coming down the pike, and it's not primarily being driven by technology capabilities in our space, but it's really sort of this sort of IoT, Internet of Things revolution. And I hate the term Internet of Things because it's sort of not clear what that is or where this market is going. But in many cases, there's sort of a bunch of capabilities that are being developed to make instrumentation cheap, in some cases maybe even disposable, easier to deploy in different kinds of settings. Not that anything is really easy, but particularly when you're working out like in the Rocky Mountains in the winter or whatever. This entire ecosystem is being driven by development requirements that are really not necessarily being shaped by science use cases, because science use cases represent a very small percent of what's driving these things for like energy use or for SCADA or for transportation systems or whatever. So we're really sort of in the space where not only are we not developing these capabilities and sort of leading the charge in terms of how they turn out, but we have to sort of work with what's available and figure out how we're going to modify, shape, and integrate that into the kinds of scientific capabilities that we have and the user facilities that we're linking together. And that's actually in many ways a greater challenge than trying to sort of work from requirements from sort of a primary perspective and using those to create instances of hardware and software. So we have sort of a bunch of science specific needs for a lot of this sort of commercial off-the-shelf hardware in terms of ability to work in harsh environments, usage limitations in terms of EM limitations or power or weight or other things. We have to be able to integrate that into the national technical and scientific sort of infrastructure that exists in terms of how our HPCs work and how authentication and our cyber needs and all that fits together. And then there's, we have differences in sort of procurement and business models and sort of expectations. And that can pose all kinds of interesting little problems that I'll talk about in a bit. So if you think about the sort of the external motivators, there's all this hype about everything's being driven by Moore's law. Data rates and data usage are exploding everywhere. And if you think about sort of IoT uses in terms of like using mobile handsets as a proxy, because it's very hard to actually identify what IoT is and sort of what the model is for that. If you look at sort of handset use, increasingly by sort of 2027, if, according to sort of at least figures from Ericsson, you're looking at about 50 gigabytes per month per user, which, just seems sort of astronomical. And if you sort of try to get a feel for like how many IoT devices are going to be out in the world, and sort of this explosion of this wireless data infrastructure that's coming down the pike, one estimate is sort of about 27 billion devices, sort of by 2025. Whether or not you believe that, what's IoT? What are they really counting? A lot of these figures are biased by sort of what industry association they belong to. So getting your handle about sort of how big this market is or how much activity is happening in this space is difficult. And it's also really not clear that ESNet's interest in this space is really driven by the amount of data that are going to come into that. We'll play a thought experiment in a little bit. But one thing that's also developing is spectrum itself is opening up and providing possibilities in a way that never has existed before. So, at ESnet, we're now working with a CBRS, a Citizen Broadband Radio Service system. And essentially what this lets any sort of business or decent sized entity become their own telco, with relatively modest investment in hardware and capability. There's interest, there's issues with this. A lot of this is still being worked out. But it's based on kind of this idea of being able to dynamically manage spectrum using a spectrum access system. So there's basically all of your radio heads are enrolled into a service online that's basically checking every 30 seconds to see if there's a license, if they have permissions to radiate. And then it's moving them between bands based on what higher priority users such as DoD may be doing in sort of the spatial area of the radio head. So this is all really, really interesting from the standpoint of like what it lets you do. Obviously you can radiate at much higher power than you can with say Wi-Fi. And so you can cover much wider areas. And there's already uses, say, for example, like school systems in urban areas have deployed these systems to provide wireless internet to children on Chromebooks in their area, kind of level the digital divide. So really interesting stuff happening on that side. Again, sort of the question is, well, what does this mean for us, right? And that's sort of the meat of the matter. So just to do sort of a half-assed, sort of thought experiment to sort of think about what this means. Sort of steady state traffic on ESnet for the past 6 months is about 1.39 terabits per second. If you take that figure, take it as true, and maybe we believe it, maybe we don't. It's an industry number, and it may not be very accurate. But supposing you're looking at handsets that are doing 50 gigabytes of data per month, well, that translates to about 160 kilobits per second, sort of steady state transmission. So if you wanted to think about like supposing ESnet went crazy, and we started to act like a telco, and basically all of our traffic was coming off wireless, sort of IoT type devices in the next few years. Basically our backbone sort of steady state would be sorting something like 8 million plus sort of North American, envision future North American handsets in sort of the 2025, 2027 timeframe. Okay, not going to happen, but it just gives you an idea of kind of the scale of what's involved here. So the big fly in the ointment is trying to figure out, well, okay, so there's, supposing there's 27 billion IoT devices, which might be used for DOS science. Well, what percent of those are actually going to like hit our network and be involved in sort of the science use cases that we're envisioning? And if it's 1 in a million, you're talking 27,000, but that's only like 0.3% of current steady state traffic, right? If it's 1 in 100,000, that's 270,000 devices, which is okay, 3.3, additional load of sort of 3.3% of current steady state traffic. So even if there's a ton of stuff happening in this space, the story here is not that it's going to like saturate the backbone or are fundamentally sort of cause a challenge, problem for our our backbone operations. And added to that is most IoT devices use far less data than we might envision for like a North American handset, because you're not downloading movies, you're not, you're basically bursting small amounts of numeric data for measurements. And then of course, the other factor is a lot of this data is actually is data we already see that may be coming over wired capabilities now, such as from inside a facility. So let's suppose only half of this data is really actually new in terms of like what gets pushed out, and as a new IoT device gets pushed out, maybe only half of them are actually collecting something that we wouldn't be getting before. So maybe you're looking at like sort of a 1% net increase in our current trend in traffic growth over time. But it could be 10%, right? Because we're playing a game of angels dancing on the head of a pin. There's so many assumptions here and there, and so frankly, we're not sure what the trajectory for a lot of this is. That it's very makes prediction very, very difficult. And that's sort of the nature of future prediction. So in the face of that uncertainty, I don't think you can make the story. What really matters is the amount of traffic. I think the story you can make is what really matters is where are our customers going and what are they deploying? And that's where this sort of IoT and our involvement in this mission space becomes more compelling. Because basically we need to follow them into this space because they are going to start deploying this equipment all over the place, and they are going to start using it to substitute for some things that may be wired at current. So right now out in the field, there's really no alternative. You're out in the middle of nowhere. Your choices, in some cases, for some programs we're working with, you're choosing between, having a grad student walk out there and collect an SD card, or maybe deploying a CBRS system and doing some other backhaul, or using Starlink or something like that. But also you're starting to see like stuff happening inside facilities. So for example, like the beamlines at Fermi, they're beginning to explore deploying a CBRS system to run robotics down the beamlines. Even in applications like at some of the NNSA labs, there's beginning to explore things like special cradles that you can put a phone in that limit how they work when you're in like a controlled area, and greater use of wireless for stuff that previously couldn't be wireless. So there's all kinds of things that are happening in this space because of sort of the natural convenience, and we saw this with Wi-Fi, right? So I've worked at Berkeley Lab now for 6 years. I've actually never connected my laptop to an Ethernet connection. It's never been on one. So you're going to see whenever people have the choice, they tend to use wireless for that last hop. But they're going to expect the same kind of capabilities and service and quality and support from our teams and our capabilities that we provide through the optical backbone. So we're going to have to, so that's really the driver why we have to get in this space. And the really way you deal with learning by, faced with uncertainty, the best way to handle it is sort of learning by doing. So by building a general capability to track, identify, and respond to what's happening in science use of wireless. So within ESnet, really, there's kind of 2 tracks of activities. This is not an exact alignment of sort of where the programs are. This is my rough generalization of kind of activities along 2 lines of effort. The first is really focused on understanding opportunities for integration of kind of ESnet 6 or 7, automation and software-defined networking capabilities. So it's really looking at sort of particularly like the 5G core itself, and how we can put overlays on top of that, how we can think about expanding the service features that we have on the optical network and in future generations of the optical network to include, intelligent routing of traffic based on the intent of what scientists have, to be able to harden the core to make sure it's more reliable, to be able to support different kinds of workflows that are unique to science through ultra low latency kinds of things, or other capabilities that are emerging and how we sort of make those work for science. The second line of effort, and that's really where I'm focused, and the rest of this talk is going to focus, I'll talk a little bit more about some of the first stuff, is really getting at sort of what are the use cases? How are scientists using IoT and advanced wireless? And then what does that mean for what our service portfolio has to look like? And so these two efforts are closely aligned. We're working closely together, and it's really a lot of fun to see this fermentation happen. But there's a bunch of stuff going underway. So to talk a little bit about that first line of effort, just a little bit, we have active sort of research underway, and this is being led by Miriam and Wenji and a bunch of folks to think about sort of how you integrate intent-based reasoning and any agent-based models / machine learning, sort of so that they can basically interact with the 3GPP core or the control systems on the wireless side to better support sort of science automation and make things like Oscars work more effectively across the wireless divide. And that's really being driven by this closed loop science that I talked about before, where you're trying to be able to collect measures, understand what that means quickly in the field, have that data move back perhaps to support high performance compute simulation running on the back end, and then push out adjustments to what your sampling plan may be based on what hypothesis you're working. On my side, sort of on the service side, not that there's a my side, I'm working a couple different sort of use cases to begin to understand what it means to deploy this capability out in the field, and learn sort of a lot of the practical lessons about how well this equipment works for different science use cases, how scientists are taking it up, and what shortfalls they're finding. A big, one of the two, and I'll talk about sort of two use cases, but the first one is really sort of an effort by our LBL's applied physics program to understand sort of urban radiation detection, to understand how do you identify when abnormal, say, sources might be moving, radiation sources might be moving around in an urban environment. How do you develop algorithms that can effectively discern between background sources and routine sources that you may see, and where something may be sort of out of wonk. And that's an effort that's also working with sort of an intelligent smart sensor called Waggle from Argonne National Lab. Really this is kind of an interesting opportunity to study sort of how 5G and wireless systems work in sort of urban areas with urban clutter. It's also partially making use of commercial networks where available. So it's figuring out sort of also how we work across sort of either networks we may operate, such as CBRS, or networks with Verizon and AT&T, and begin to sort of figure out how that all plays together. We're sort of in the process now of the first set of Waggles are getting put up around LBL, and then we're beginning to think together sort of how we support the scientists who are doing this as they think about deploying sort of other places in the Bay Area and also back east. Second use case that we're involved in is really sort of environmental and field science, and this is really getting at where the first case is looking at very, very rich networks where power is available, radio heads can be put where you want them, you can have good coverage from commercial providers. So there's that a lot of the problems you have in deployment and a lot of sort of the engineering challenges you have in deployment don't exist. The second one is really looking at a very sparse research environment where we're working with the SAIL program to support environmental field science in Colorado outside Mount Crested Butte. Basically what's out there is there's an outdoor observatory that has 600 or 700 different instruments deployed in different sensor fields sort of throughout this area, which is quite large and very empty. So they've long sort of had this problem of like, well, how do you deploy this stuff out? How do you bring the data back efficiently? And so we're working sort of the process of trying to design, well, how does the network need to work? What can we deploy? And it's a very different engineering challenge, because what you're really trying to do is how bad a wireless network can I deploy and have it be good enough? Because I'm going to be putting my radio heads with very low density. I'm going to be I really will not going to be able to optimize my throughput. I'm not going to be able to sort of optimize my power use. I may have to like ration power to devices and turn them on and off based on power and what I'm able to get through solar panels and batteries. So there's a bunch of sort of associated problems with supporting, sparse field science, but making it good enough to support that vision of sort of data seamlessly coming out of the field, being able to inform simulation models, and then down the road, being able to push analytic informed changes to sensor modalities or to sensor placement. And this is an interesting also problem because we're working with Starlink to explore how we can use that as a backhaul mechanism for a CBRS system. And I'll talk about that in a little bit. So this year has been very busy, just beginning to sort of get into the wireless space with deploying our own ESnet CBRS system. We've procured and have just almost finally completed deploying Nokia CBRS system at LBNL with the core at LBNL and one base station and a couple of radio heads here on the campus to support some local projects here and some explorations we're doing here with coverage and understanding how these work under different conditions. But then we're also going to be deploying a baseband in June out to Colorado, along with radio heads and other equipment to build sort of that backbone network that those folks need. And along the way, we're beginning to dabble a little bit with some other technologies like LoRa, millimeter wave panels, and we're also looking at Starlink, and I'll talk a little bit about what's going on there. So what's really cool here and what kind of blows my mind is like how little equipment it takes to now become a telco. Basically with like, sort of 5U of equipment in a rack, we are now a telco. We can issue SIM cards. We can put those SIM cards in any device that works on band 48 and is within the range of a radio head, and we're off to the races. So what you have there on the table, that one photo there that I can't see because it's behind everyone's pictures, is those are band 48 radio heads that are waiting to get deployed. And then the central core right there that's a shot of the equipment before it was completely racked. But basically it's a standard off the shelf equipment. It's a Juniper router, it's an HP standard server in the middle, and then a Nokia baseband unit. It's pretty amazing how that works.
So we had one question.
Oh yeah. Sorry, I couldn't see it.
For a second. John Graham wanted to know: are you looking at using IETF Alto services in your 5G core?
No, not yet. But I'd love to talk more about that. Is that something you're looking at?
So let's see, John, I can probably just unmute you if that's easier. If I can find you on the, he's looking at it. I'm gonna unmute you, John. So go ahead if you want to talk.
Or I'd love to take it at the end. Oh, go ahead.
Yeah, I was just making my room a little bit quieter. Yes, we are looking at using IETF Alto services for bottleneck detection and route suggestions.
Cool.
Yeah.
Could we loop up afterward? I'd love to learn more about that. Would be really cool.
Sure.
Thank you very much. Yeah. No, hadn't gotten that far, but love to. So where we're deploying in Colorado, to get back sort of this Colorado deployment, is there's actually no connectivity back. So we've procured 3 Starlink terminals, and we're in the process of deploying those at a couple of sites, and I think about some photos later in the presentation about what that looks like. But actually, what's really interesting is CBRS is becoming something that the existing telcos and a wide variety of other sort of service providers are getting into. In fact, there's even a case of a wired internet provider beginning to deploy CBRS-enabled boxes at subscribers to basically provide a turbo boost. So where they're limited by, I guess they're putting an ISDN or whatever copper. They're actually using the CBRS wireless side to provide this boost of capability for users when they have a peak in data movement. And there's all kinds of other things happening with CBRS. One of the things that's being done, particularly with some telcos in Asia, is people are deploying CBRS-like instances to provide coverage to, say, remote islands or small communities where it doesn't make sense to roll out a big cell tower and make use of licensed spectrum when you can just roll out a small amount of equipment and set up a small mast and put a couple of antennas on there and use CBRS space because there's nobody else using it, and support coverage that way. And so what some of those companies are actually starting to do is backhaul that CBRS traffic via Starlink rather than pulling fiber to the network cores or baseband units. So we've been exploring with Starlink about how we can take these terminals and provide kind of a laboratory, and share the data from that as we're using it to explore this one scientific mission. They're sort of interested in using sort of the clean network that ESnet has to sort of see, well, how good can this performance get? So Starlink is now basically, depending on what kind of deal you have in place, sort of available everywhere in CONUS. I'd just like to say, by the way, this is a map right here of sort of this Starlink service regions. But every time I see one of these diagrams, my mind is totally blown. This right here is a chain of Starlink satellites that's, basically sitting in a deployment orbit, before the satellites all do their phase change burns to deploy to their specific orbit. And it just amazes me to see like 50 satellites in a chain like that. So the initial workflow for what we're doing in Colorado looks something like this. There's a bunch of sensors out there in the environment. We're basically enabling sort of this arrow here, which actually becomes sort of a bidirectional arrow, where essentially we're going to have solar powered stations that are using cradle point routers sort of close in to the sensor fields. And then there's going to be a sort of a whole set of fun engineering and spitball and gum and chewing wire effort to understand better how one needs to work with the different routing, the different logging systems that these sensors have. In many cases, they're proprietary, or they work in their own ways, or they don't have Wi-Fi or whatever. So there's going to be a lot of fun kind of working through some of these issues and figuring out, well, what does it actually take for these formerly isolated places to become part of, and tied and linked to sort of ESnet through this wireless edge. And a lot of it won't be very, it's not sort of cutting edge. It's really sort of figuring out these engineering problems. And there's been a bunch of folks from sort of USGS who've gone down some of this path before, who've been very helpful in sort of helping us think through how to harden stuff and how to deploy stuff. Those cradle point routers and those solar powered stations will be then connected to our CBRS system to backhaul the last few miles. And then that will enable then data sort of to regularly hit the sort of East River database. This is actually hosted on NERSC, and then be used by sort of a variety of folks here. So, our effort here is really to sort of tie together this piece here that's missing. And this is just another diagram of the same thing, just sort of showing how the connectivity will work through Starlink. Starlink are initially will be grounding through Seattle 6. And that's kind of where the traffic comes out of Starlink right now for much of the CONUS area. Starlink right now is running Google Fiber for their back end. So we've also been trying to explore with Starlink about, sort of what their long-term pairing plans are and understand sort of what their network is going to look like, so we can understand how best to, as more scientists become users of Starlink, how we want to sort of manage our pairing process with them. So a lot of fun there, and it's been really interesting to sort of learn more about their backend and what they're doing. What's sort of insanely cool about all this is along with sort of this capability to deploy stuff to becoming your own telco, there's really sort of an ecosystem of support and management tools that are starting to become available. So I mentioned previously, the whole secret to CBRS success is this ability to enroll radio heads into a spectrum allocation system, a SAS. and that handles sort of the constant deconfliction of use types and priorities and channel overlap. What's neat is you're starting to have an ability, if you have this kind of capability, and you've gotten the SaaS license, become a certified installer, is you can begin to then sort of plan out what your wireless networks are going to look like and what their coverage is likely. And this is sort of just a screenshot from Google has a SaaS tool. Google is a SaaS, and you can begin to sort of chart out sort of what your coverage is going to look like. And part of what we want to do in the field is see, well, how accurate are these these predictions, and what kind of performance do we actually see when we do this. And then, we are, once we've done this, we are then now, ESnet is essentially a kind of a distributed telco, in that we will have a couple of base stations in different places. We'll be managing them remotely, and learning a lot of lessons about sort of what it takes and what's involved with it. And so, I'm really sort of excited for this next year and kind of what we're going to be able to get into and do. So, our rough schedule is, we were hoping to have this sort of the CBRS radio core and everything deployed in April. It's actually sort of not going to happen sort of till the end of May. It's taking a little more time to just work out some of the kinks. But that's actually important lessons that we're trying to capture as we do this. And then we'll be doing a campaign to install equipment in Colorado in really now it'll be late June, July. This is actually a picture of one of our Starlink terminals that's now deployed at an ARM radar site in Colorado. And then sort of in the summer, we'll be doing a bunch of backhaul and network testing and just beginning to explore, like, okay, what's the power situation? Is it adequate? Are we keeping stuff up enough of the time? Are we getting enough bandwidth? We're going to be doing, we're going to have to deal with foliage. We're going to have to deal with like how we can place the antennas and limitations on that. We're going to deal with limitations on how many solar panels we can deploy and how we manage all that. And that's going to be a lot of fun and really interesting. And then sort of we're going to be doing a summer sensor connectivity campaign in August. And when I say we, by the way, there's a number of other folks kind of working on this. So Sten Wiedlea from ESA is sort of our partner, and Cheru with ESA, and Dan Feldman and other folks. And then sort of within ESnet, really gotten a lot of help from Nick and Chris and a bunch of folks. But then the hope is that we sort of have a full network up sort of operating in the October timeframe to support kind of this backhaul process, and then we'll operate it for a period of time to learn from it and see over time as new services become available. And so on the optical side, how do we want to tie this together? So there's a lot of lessons learned kind of from this process in terms of practical lessons. Those sort of vary all the way from the mundane to the important. Lots of little ones, like there's just a lot of difference in sort of like, telco reliance on DC power versus what we traditionally do, although a lot of our Nokia hardware is DC power as well on the optical side. Getting precision time signals to equipment in our racks, just little things like that have taken some time. Plugs, getting our folks happy with the on the electrical certification side with this equipment that's coming in. This is the first time a lot of them have dealt with sort of telco kinds of equipment. So we actually had to spend some time taking apart the electrical converters for the radio heads and making sure everyone is happy with how those worked. Because we're running a non-standalone core on the CBRS side for now, though we may decide to change that in future years. Getting folks happy with kind of and how we want to isolate and protect ourselves against managed hardware that's in our racks that we're accessing, sort of outside our IP space. And then big thing is design for deploying resources in sparse conditions, and like sort of learning from the community that's been doing this. But also to understand sort of how, like, what does that mean when we're deploying stuff that's going to interact with our equipment and our network on the optical side. And this is something that there's sort of this community of field scientists at the USGS have been really, really helpful with. Supply chain issues, doing this during pandemic has been enormously frustrating. I'm just mentioning that for sort of therapeutic value, but it's again, it's interesting. And there's little things like getting SAS training, getting certified to be able to place radio heads, onboarding on use of this equipment, how it works, understanding what its basic design assumptions are. And then, down the road, we want to begin to coordinate with there's a lot other CBRS and similar kinds of activities happening at other labs, or throughout the complex is really what I mean. And really what we want to do is begin to coordinate with them. In some cases, we'll be operating a CBRS core, but it might be nice for like devices to be able to roam between, say, one lab and another lab. And so we want to be able to think about like how we might make that work and how we want to use our network to support that. And things like beginning to develop performance monitoring and measurement capabilities, and that ties to a lot of other things that are happening sort of within ESnet, other development efforts. The big thing is sort of bringing the community along the shared spectrum journey. CBRS and SAS, that whole technology is in early days. This was only sort of started in 2019. So from an actual implementation standpoint. So we're all in this process of trying to figure out, well, how well does this vision work? And there's already sort of work going on in the community and other places to begin to explore, well, does the SAS framework need to be refined? How do we think about improving our models for propagation and handling interference? And then working pairing with Starlink and sort of longer term research. And there's going to be a lot of other non-terrestrial networks that get deployed. So AWS is working on Kuiper. There's a number of sort of small sat IoT optimized small satellite constellations that are starting to get deployed. I live in Alameda, California, and there's a launch company called Astra that's down the street that's trying to get into that space. And so understanding what that means and how that's going to work is going to be fascinating. And then, the technology space itself is really flexible, even on the telco side. So there's a lot of different design configurations for what 5G is and how 5G is deployed. And as part of that, there's also a lot of work going on in terms of how you think about deploying services and edge compute resources, even in the conventional telco space. So keeping sort of our hands on that and understanding how that works and being able to reconfigure our own research network and figure out how we want to support that is going to be really interesting. And then figuring out how we align those deployment cases, that hardware and software deployment cases, with different scientific use cases is going to be fascinating as well. So in terms of sort of long-term trends, we're also working to sort of align with DOE science strategies. There's things happening within DoD with the Federal Mobility Group. There's a national strategy or a DOE strategy for 5G that's in development, just starting. And there's a lot going on the DoD and DARPA side of the house. And I'll talk a little bit about that. But spectrum allocation itself is sort of, we're at Gen 1 of how that system works. And definitely there's people in urban areas particularly are finding kinks and issues with SAS accuracy and performance, and having hardware from different vendors kind of step on each other. So there's going to be sort of changes in how that works most likely. And then thinking about sort of spectrum use policies, probably the amount of spectrum available for this type of shared spectrum stuff will increase over time. I think there's other bands that are being looked at. And then of course there's white space bands that people are using for similar kinds of things, particularly in the IoT space, some of the old television spectrum. And then there's this increasing use of wireless for traditionally wired activities, and sort of changing acceptance of technical options and sort of design assumptions. So for us with ESnet, what does that mean for our service model, right? There's a ton of different ways, and maybe we'll do some of all of it, right? But there's a bunch of different ways you can imagine providing sort of service in this space. So at a minimum, it's providing information and being able to update things like faster data, and begin to sort of provide information that will help scientists when they're deploying their own network or their own CBRS system, or their own millimeter wave or whatever, integrate with us and do it effectively. There's also, providing performance support, and traditionally we've done that through providing, really excellent monitoring tools and perf sonar. And there may be, versions of that you want to deploy sort of at the wireless edge to be able to explore your connection. It's providing design models, and that's something that we've been doing on the optical side now with Science DMC, and how DTNs are configured and how they can be tuned with things through like the data mobility exhibit and all those exhibits. And one can imagine doing similar things on the wireless side in terms of providing design patterns. There's, providing wireless access service. So, it may be that, we're helping to support, when someone's deploying a CBRS system, maybe they own the CBRS system, but we can help them because we've deployed a couple of the systems at that point, get up and running efficiently. And then finally, sort of at the extreme end, there's sort of like providing wireless access. We have a very performant national optical backbone. And it could be that what we want to do is in some cases provide the ability for someone to, or we provide a baseband unit and radio heads, and we connect that into our core, and we manage that set of wireless resources for someone as they're conducting a campaign. And then when they stop doing that, we take it down and move it somewhere else. And so like I could see all of these services sort of happening depending on what makes the most sense for both for science and for sort of what we need to do. So technology, sort of things to watch if you're interested in this space. DoD is a huge gorilla here. They're putting like $750 million into like 5G for battlefield uses. And that's going to cause a lot of spinoffs that may be really interesting for science field use capabilities. So, really rugged equipment, CBRS systems in a box, more efficient power, alternate power sources, batteries, sort of integrating satellite and terrestrial systems. There's work that DARPA is doing to begin to like automatically make use of whatever part of the RF spectrum or whatever networks are available for messages. Sort of increased merging of commercial and other infrastructure as you sort of start to see cloud providers actually beginning to provide CBRS instances sort of in a box. So for example, AWS is I think just about to, or is already, they've for a long time they've had a service called Snowball, which would ship hard drives to a location. You basically fill up the hard drives and ship that back. And what they're actually doing now is providing basically a managed CBRS baseband unit and radio heads where they ship that out to you, you deploy it, you connect your devices, and your data flows automatically back to AWS storage resources. So there's all kinds of different service models that are becoming available in terms of how you think about this technology and how it gets deployed. And there's a proliferation of small sat and LoRa and all kinds of stuff. And then there's also a lot of MVNOs getting into the space to repackage commercial capabilities. So there's stuff like Helium, which are providing rates that are very attractive for IoT uses. So I think basically as long as you're basically you can set up a device for like, I don't know, 30 or 40 cents a month. You can put a SIM card in it, and as long as your data rate stays low, it's very, very affordable. And then once you start to get close to a gigabit per month, it starts to become pretty expensive. So if you're deploying a sensor field and you have commercial cellular, those kinds of MVNOs may be a really good option. And I've got a picture here of actually, this is new-ish Nokia equipment. This is actually a picture of Nokia's lunar. They're putting a CBRS instance is slated to go to the moon on a commercial lander that's happening in the next few years. And this is actually their hardened lunar CBRS core, and then a radio head and a terminal unit. And basically they intend to use that there to instrument sensor fields as our lunar presence begins to grow again. So conclusion, and thank you. This is, we're probably going to do a little bit of everything in this space. Sort of that's the practical strategy is to, because there's such a wide range of outcomes in terms of how this technology is going to grow, in what form, in what technology, in what specific sort of radio wireless instance it's going to use. In some cases, I think we may provide the wireless edge, but I think in a lot of most cases we probably won't. We'll be using sort of existing commercial resources and then trying to figure out how we integrate with that almost successfully. But it's important to have experience sort of across that range of services so we can figure out when someone is coming to us with a data mobility problem, how we can best support them. Definitely we'll be working with sort of traditional players and the traditional telcos like AT&T and Verizon and then some newer ones like Solona to better integrate sort of science workflow and services via sort of the APIs and other things that exist now in the 3GPP core. Obviously, this is something where we cannot collaborate enough. I would really love to know about efforts that folks here on this call may know about. Very happy to loop up and share whatever it is we're learning or learn from experiences you have. And with that, thank you very much for your time.
Thank you so much, Andrew. We did have one additional question come in. Will Starlink support low raw WAN? I guess that's the way to say that in the future. Will they allow us to run SRv6 in the satellite mesh?
So in terms of LoRa, I don't know of any plans for Starlink to sort of operate on LoRa frequencies. Sort of LoRa is kind of, there's two bands. There's one in the 600 megahertz and one in the 950 or something. But that said, never say never. I mean, I don't know. Maybe they could. LoRa equipment is really cheap, and maybe you can include the LoRa antenna and bring it along for the ride. Their satellites are operating up, I think, around more like 14 gigahertz or something. So it's not the same spectral range at all. Sorry, what was the other?
Will they allow us to run SRv6 in the satellite mesh?
Oh, I don't know. I don't know. Yeah, Starlink it's hard to get in comms with them, and it's hard to know necessarily sort of where they're going. Not because they're especially secretive, but because they're very lean. If I have a chance to ask them, I will.
Okay. And I guess my question is less of a question, maybe more of a statement. If there's anybody out there that's from the RNA community that's been looking into this and you have any interest in working, maybe just indicate in the chat room so that we can follow up with you afterwards, since this is really an emerging area. And I know a lot of people are excited to understand how it would work. And for many of the regionals, there are just pieces of your world that you need to serve that are not served well by regular connections. So this may be an option in the future. So I'll just pause right there if anybody does have any other questions or statements that they want to stick into the chat room. And while we're pausing, we will not have a talk next week, but we will have Marcos's rescheduled talk on the 27th. And he's going to be talking about Kata containers and how he's using them to do some DTN work. John also says we are actively building 2x GNBs to deploy.
Oh, cool.
All these acronyms that I have no idea what they mean.
Yeah, are you using a CBRS system, or what are you?
Let me unmute you again, John, since it's probably easier that way. All right, you can unmute, John.
Yeah, we're duplicating the Barcelona Mobile World Conference demonstration, Xilinx T1 with open air interface for
Cool.
over the air end to end. So we've purchased 2 T1s and then 2 T2s, and we plan on deploying at NYU on the East Coast and UCSD, and linking the 2 sites with Sense AutoGoal. And having a common 5G open area interface core running
Oh,
in a
cool.
Kubernetes cluster
Okay,
that's already distributed to both campuses.
that's great. I would really love to learn. Can we loop? Do you want to put your email in chat or send me an email?
Sure.
That's really cool.
Yeah, our goal is to use Sense Auto Goal to plumb multiple campuses together and do 5G core interoperability tests, because there's at least 3 I know of.
Are you using different vendors, or are you going to work with the same?
Currently, we're just going to reproduce the Xilinx T1 on
Okay.
open area interface.
Okay.
They're using Multis CNI to get IPv6 and segment routing, but we want to throw that out because our Kubernetes dev cluster is already running Calico VPP that gives us SRv6 and VPN6 and several other shiny
Cool.
features.
Yeah, I would love to loop up. So if you're available, let me know.
Yep, I have time right after if you want to continue.
I think I've got a conflict, but let's you're on next week?
Yep.
Okay, cool.
I just put my email in chat.
Thank you.
All right. Well, with that, then I think I will adjourn us for today. Thanks everybody for joining, and we'll talk to you in about 2 weeks. Thanks all.
Thank you.